Hey guys, Stanford here with the Fun Robotics Network, and welcome back to an episode of Behind the Bumpers. And today I'm hanging out with Team 254, the Cheesy Poofs, here at Cheesy Champs, and we're going to be taking a look at this crazy machine that they've got here, going through their entire coral journey from their ground intake, the serializer, their end effector. We're going through their climber, drive base, all the decisions they made to get to those points. Also been going through all the software that powers all of the crazy stuff going on with this robot. So stay tuned for a look at all of that and more on an episode of Behind the Bumpers.
This video on fun is brought to you by our viewers, supporters, members, and also in partnership with the following. First Team SolidWorks is free for you. Design in 3D, build your robot, and gain the career-ready skills 80% of employers look for when hiring engineers. Get SolidWorks for your entire team when you go to solidworks.com/first. Did you know that Fun has awesome merch options, including game-themed merch available at funroboticsnetwork.com/merch? From cute thematic options to robots and fun-themed apparel, you can directly support Fun and look good at the same time. You can also become a Fun member or supporter through YouTube Join to get early access to most of our content. Thank you for your continued support.
All right, Ryan, go ahead and take us through the coral journey that this robot has.
Yeah, of course. So the first step in the coral journey is the intake. I'd say this year at least this is one of the most unique intakes that exist, from the composition of the rollers, like even roller placement, to the 4-bar linkage that drives it. We've optimized this intake basically as much as we can for both speed and robustness, which has led us to like some very interesting design decisions that a lot of other robots didn't follow. So I'm going to start here with the rollers. These rollers are very unique. So something pretty early on we noticed is that a lot of other teams, like we saw prototyping videos about things like teams using star wheels as their top rollers, but from what we saw, the star wheels just seem more of like a suggestion to the coral than an actual like a real top roller that will tell the coral where to go, basically. So the foam here it's designed to be like to have almost as much grip on the coral as possible. So the West Coast product silicone on top of this roller has an extremely high coefficient of friction onto the coral, and then the foam further allows the silicone to compress over the corals to get extra surface area. So on the bottom here, the kicker roller is also made of foam, because something we noticed also pretty early on in the season is that more solid rollers just had to grip the flat face of the coral instead of just being able to pick up the bottom like this roller does. So as the coral progresses up after the coral like goes through the top roller and whatever, it goes through these belts. So these belts here, we put them here because on some of our early intake prototypes where we had a middle roller, the coral kind of had dead spots because it's a very hard game object. So these belts it's a lot lighter than a middle roller here. It's faster, and it prevents dead spots along the way. So this top roller is much less complex because it doesn't need to have too much grip on the coral. So it's just silicone and some gaffer's tape to mainly hold it. And then we have some pretty stiff funneling wedges here just to get it all the way to the indexer. And then so we also drive the intake up and down. It's a single pivot point deploy. We drive it with a 4-bar linkage because, in our opinion, with our testing, it's a lot lighter. It saved almost half a pound versus just running number 25 chain, and it gave us a lot more freedom on where we could put this large 1.25-inch OD pivot axle. So we're gonna move on to the indexer now. So we have on the front here, we have some cut 60A wheels. So these are 60A 1-inch thick flex wheels. We have they're notched like this. They have a cutout here because, well, for one, it has to fit in the frame perimeter, because otherwise it sticks out. But also it allows it to pick up the coral edge kind of on here and like force it to go up. And then we have a beam brake sensor here just to determine like so we know when we have the coral. So next up here, we have these 3 sets of some half cut flex wheels. They also have notches just to grab the coral. Something we had earlier in the season is at our first 2 competitions, when we still had our funnel, these used to be star wheels, but from what we found, the star wheels weren't really stiff enough. They didn't have enough authority over the coral to really like get our autos the speed we want when we still ran our autos off of our human player load. So we also have this top plate mounted here just to prevent the coral from popping out of the top from the intake. And we also have standoffs here to prevent a match ending jam condition. Something else we added after the championship is, because we removed our huge human player loading funnel because we thought because we didn't really use it at the championship, we added this second top plate here in conjunction with this to keep the coral down, like where the funnel normally would have kept the coral down. And then so the final stage here in the coral path is the end effector. So this is also a very unique thing. So something we designed this for was to be as light and as fast as possible. So this is an entire redesign from what we had at our first competition and in our first robot photo. So this is the first end effector we had was about 11.5 pounds. This is closer to 9. So we saved a ton of weight in the end effector, because this is the worst place on the robot to have weight, because it just being able to flop around like this means our robot was very tippy and slow. Something else, we have this deployable L1 hard stop that deploys automatically when the wrist retracts. So when we go down like this to our handoff position, the coral will hard stop against this, so we can keep our rollers running all the way, and it's a known set position. So our algae here is driven by this top roller here. So this is a 3-inch stealth wheel, and this just grabs the algae off the reef. We have these like rubber teeth, I guess, on the bottom here, just to prevent the algae from slipping out on the polycarbonate. And a fun fact about this L1 hardstop hoop here is it's made of titanium, because aluminum bent too much and steel's too heavy. Some other things about this end effector is we have this sort of V funnel here, just to give us a little bit more working like room to play with on our auto align, because normally the inside of the coral is 4 inches wide. This gets us for it to be effectively 6 inches. So we have an inch extra on each side, that if the pole will hit here, it'll still score. And then for the scoring, we have we have a beam break sensor here that will detect when the pole or when the coral is on the pole, and it will just shoot the coral out onto it.
All right, awesome stuff. Let's go ahead and hear about the rest of this robot.
All right, yeah, so moving on toward the drive base. This year we chose to use the X2I's X1 gearing, and we actually swapped the drive pinion to a 10 tooth just because of the short distances and fast acceleration. And like a lot of other teams, we also use X44s for the Azzies. And yeah, and our drive dimensions are 29.5 by 29.5 just to reduce tipping. And we're using 3x1s again this year to lower the CG. And this year we actually tried something new. We were running 2 can chains, one for the drive base and the climber, and another one for the superstructure. And you can see for the elevator mounting, we have a 2x1 running across. This is where the A-frame of the elevator connects to, and we have core 20s running through the bottom and bolting into the elevator A-frame. And then we're sending wires underneath that, so it's a little bit lifted off the belly pan. And then we have the battery in the center of the robot just for CG reasons. And then if you come around to the front here, you can see we have can ranges on the Limelight 3D print, and that's just, we'll talk about it more during software, but that's to allow us to detect how far we are from the reef so that we can auto stow without having to wait for the driver to stow manually. And yeah, we're using Limelight 4s this year, and we had problems with cooling the Limelights because they were overheating a bunch, so we're using Noctua fans. And we have a heatsink on the back just to stop them from overheating. And then we also have these coral protective panels on the bumper, so it doesn't count towards the robot weight. So they're bumper panels just to stop the coral from going towards the robot. And then something special this year, because the bumper rule changed, we're using a lot denser foam. So this is 3 pounds per foot, so it's a lot heavier in general and firmer. And so the bumper is 15 maxed out, and we're adding steel plates here just to get us more weight. And then for bumper mounting, we just have CNC blocks over here with lock nuts that are counterbored into the mount, so it stops the bumper from racing up. So if you lift it, you can see like the bumper strapped in there. And yeah, that's pretty much all for the drive base. Moving on towards the elevator, we have an A-frame this side. It's actually pocketed on the inside. I'm not sure if you can see that, but it's pocketed on this side. That side was originally pocketed too, but because of structural reasons, we left it unpocketed. And these A-frames are all welded, where we had inside gussets here. These gussets used to be the mounts for the funnel, which we removed for the off season just because we didn't use it at all during champs. and yeah, that freed us a lot more weight, and we just didn't use the funnel in general that much. So if you see over here, you can see there's the A-frame is welded to the end plugs for the connecting to the elevator, and then there's screws running down the inside that connect this billet mount. And in general, our elevators 2x1s with 16th wall, and they're all pocketed, so you can see the inside of the tube. And one of the elevator changes we made later on in the year is that these are welded together. So this is the cross frame for the elevator. We added this on after our first regional, and these are welded. They used to be just pinned and screwed, and we did this for structural reasons because the climber is mounted on the A-frame. That was torquing the elevator a lot, so the whole elevator was shifting. So we added this. We also increased these the surface area that how this clamps on, and then we're also using these SDS bearing rollers, and we have some custom SDS bearing rollers too up here, and that's just so that we can get more mounting area and also have pulleys in the tube. So for how we're driving this elevator, we have two X60s on the bottom of the elevator, and this is all continuous rigged. Yeah, you can see a better view over here. So this is all continuous rigged. So we have belts in the tube running it, and then you can see we have 36 pulley drum, and then the pull down belts are just running along there. And yeah, so another change we made during the season just from testing is that we had sorbethane on the bottom. That's just because of how hard we're driving down the elevator. We actually snapped a few belts doing that. And yeah, you can see like sorbethane sometimes around the hard stops, so that was just to stop the belts from snapping. And then for our top hard stops, these are Delrin, just because we didn't want the aluminum clashing with aluminum. So you can see we've had a few of these brakes, so we've added a bunch of rivets on there. And then yeah, these are also custom. These are our top hard stops, and we also have pulleys in there. So these are dead axles for the pulleys that are running in the tube. You can see some of the pulleys here, and yeah. And another interesting fact we had for the elevator is that we have 3/8 steel plates that are actually in here, so that we just have more surface area for the climber. So we have screws mounted through here, and there's steel on the inside, so that when we're torquing the climbing the elevator's torque, so we have more surface area, so it's not just all concentrated on one spot. And then yeah, that's pretty much all for the elevator. So moving on to the climber, this climber is the gearbox is actually located on the drive base just so that the weight's lower down, and we didn't feel like we needed it up here a lot of the time. So it's Dyneema driven on the bottom. You can see a better look at it over there. So the overall idea is it's a Dyneema that spools one way the whole direction the whole time. So then there's a ratchet on here too. So you can see there's a ball over here, and then there's a ratchet over here too. So the climber spools only one direction, so you can see it unwind and then rewind. And yeah, that's how basically the climbing motion. And then moving on to these plates were originally 60-61, but we found a lot of bending in them, so everything on here is 60-61 except these two latches, which are 3/8 60-61, and these two side mounting plates, which are all 60-61. And we added this structural member later on in the season just because of how much torque the climber was applying on the elevator. We would see the whole elevator tipping over, so we added this just to stop the compression on the climber. And then moving on to our actual latching device. So this was inspired from a double rotary latch. So you can see there's two latches over here, and then the pull comes in and then it latches here. So it's stopped with these pawls over here, and then that's also how you release it. So this is all sprung over here. And then we also have limit switches, which were used to detect when we actually have a cage in. So we have auto climb. So whenever the cage is actually fully in the latch, it auto climbs by itself. And then these were originally for the to avoid collisions with the cage and the elevator, because if the cage moved over and we were climbing, it would hit the elevator. And this one was for the funnel, but as I said before, we took it off just because we weren't using it. So not really necessary, but we just left it on there. And everything on here is passively sprung by a 30-pound gas spring. That's just so that it automatically deploys when this the spool is unraveled. Yeah, that's pretty much it for the climber. I'm gonna hand it over to software. And
all right, for software, we can start with our pathfinding, which is probably where the most of our time went this season. So for pathfinding, we're using a slightly customized path planner library for on-the-fly path generation, and this is what we use in both auto and teleop. So we can start with auto. So because of the computational overhead that on-the-fly generation inherently has, at the start of the match, we have a warm-up routine where we basically pre-compute these paths while we're sitting on the field in disable and cache them so that we don't have to recompute them at the start of auto. Additionally, for auto, we can select any branch, and we have a score sequence that allows us to choose which branch and which score level we go to. And another really cool thing about the path planner library is that we have custom nav grids, which basically allow us to determine which possible grid points the robot is legally allowed to pass through. And this allowed us to obviously not only just block out the reef, but we could also block out areas like the lollipops. Like, for example, back when we were running our funnel for four-piece auto, we didn't want to knock over the near side lollipop to risk like an algae ending up between us and the reef. So we actually blocked out that lollipop area in the custom nav grid. So moving on to teleop, we have 3 controller modes, which we can go through later, but these controller modes are designed for different aspects of the game. And each controller mode has different bindings, which kind of allows us to still manage having one driver in such a complicated game. So our 3 modes are Coral, Algae, and Coral Manual. Coral is where our primary Coral scoring happens. It has a lot of cool driver assists like auto align. We have closest face auto align for our Coral mode as compared to our auto, where we can go to any face and branch. And then for algae mode, that's where our primary algae scoring occurs, both in the barge and the processor. And then finally, Coral Manual is basically a mode that we use when something's not going right. In Coral Manual mode, we have disabled auto stow, disabled auto align, so it's relying just on driver input in case something like vision has gone wrong. All right, and we can talk quickly about some of the cool features we had for software this year. So obviously we just covered auto align. Another cool thing we have is a heading lock, where as soon as the coral enters any part of this robot, we automatically snap the drive base's heading to the closest face, and this kind of saves time, and it allows the driver to not have to align to the face after they're trying to score. And some other things that we have is we also have a heading lock for the barge and algae mode, and we additionally have a auto align reef intake for the algae, both L2 and L3, and we can use the same button for both because we already know which level the algae is going to be on. And some more some non-driver related features we have is this is the first year where we were using candies for our banner sensors. And the candies have a feature that allows us to map the candies reading directly to a motor, directly to a motor's hardware limit switch. And this gives us a faster reaction time than the banner would traditionally give us. We save approximately 50 to 100 mils every cycle. When you can see when this score banner gets triggered over here, we are automatically using, sure you can point at it, but when that score banner gets triggered typically by the branch, this is mapped directly to our Coral Roller's hardware limit switch, and on the hardware limit switch we set it to we reset the position to 0, and we position set point command it to a non-zero value, which essentially is a hack to get the roller spinning faster than it would traditionally be if we were using the regular banners reading. And then Shoria briefly touched on these can ranges. These can ranges allow us to auto stow after scoring pretty safely. Earlier in the season, we were going just based off vision, and we were checking when our pose is far enough from the reef to bring the superstructure down. But due to some pose issues for vision, we realized early on that we run a pretty big risk of climbing on the reef or stowing our superstructure on the reef if we relied on only vision. So we had added these 2 can ranges on both sides, which will look at the reef face and also let us know if we're clear. And I can pass it on to Max a little more to talk about how our vision system works.
Yeah, so this year we're using 2 of the new Limelight 4s right here on the front of the robot. That's all we have. And in addition to obviously the cam ranges, the Limelights serve to basically for the auto align and a ton of other features as well. So basically we're using MegaTag 1 this year. We tried MegaTag 2 by using one of the IMU modes, I believe IMU mode 3, basically filtering the filtered MegaTag 2 yaw estimates into MegaTag 1. But that didn't work out well for us just because the integrated IMU within the Limelight wasn't that accurate. So we stuck with MegaTag 1. And basically what we have is each camera will produce a MegaTag 1 pose and a timestamp. So we effectively synchronize the timestamps by either fast forwarding or like reversing to make sure that they're synchronized. And then, well, first when each MegaTag produces a pose, we don't just send it immediately, right? We have some checks to see if it's bad. For example, if we're using just one tag, we'll make sure that the tag isn't too small or that there's no ambiguity, because that would lead to accepting like a bad pose, and we don't want that. But also, if we have like some sort of Z level that doesn't seem very accurate or realistic, or actually we check also if the robot is rotating at I think 5 radians per second. If it's rotating more than that, then we'll just throw out the estimate because it's unreliable. And yeah, when we have the 2 accepted MegaTag estimates, we don't just immediately fill them into the estimator. What we do is we actually fuse them together into one one field pose estimate. And basically how that works is we have an inverse variance weighting for X, Y, and theta. Actually, our theta is like variance weighted vector averages. And basically what that means is we don't end up kind of like double shooting vision, or we don't end up having some sort of overestimation issues. And it allows us to, if we're working with just one pose, it ends up being a lot cleaner if we end up doing that inverse variance weighting. In the case where we only have one tag, if it's an accurate tag with where it's big enough and there isn't that much ambiguity, we'll go ahead and accept that. And we can sometimes use the heading if it's accurate. In other cases though, if it's just not as good of a measurement as we want, we'll keep the translation, but we'll just throw out the heading and we'll fall back to the gyro for the heading in that moment until we end up seeing more tags, and then we can resort back to MegaTag 1 from both the left and right cameras. But there are some points, for example, in our auto routine where we just don't consider the vision and we just fall back to the gyro heading to make sure that we're getting accurate poses, because if we accept a bad pose, it's going to throw our whole auto off, and that's not going to be really good. But yeah, overall, I mean, I feel like MegaTag 1 has been we've been pretty happy with it. We did have to kind of like decide when to use vision, when to rely to the gyro, because if you're sending bad updates to the pose estimator, we're just not going to get a reliable estimate. And it's a lot more important in general to have fewer precise estimates than end up accepting a bad pose. So that'll just throw off our whole autonomous routines and all the auto align stuff that's talked about. But yeah, overall, we've been pretty happy with MegaTag 1, and it's allowed us to get some pretty cool autonomous routines, including that 5 coral. So we're pretty happy with this year.
All right, so now we're going to walk you through our coral poses and somewhat of what a traditional system check will look like. So as you can see right now, our LEDs are cyan. That indicates our coral manual mode that I mentioned earlier, which we use in the pit to disable auto align and be able to safely test in the pit. So I'm going to feed one in. All right. So this is our L3 pose. This is our L4 pose. This is our L2 pose, L1. And we're going to shoot it out. All right. So yeah, this is green, which is our algae mode. We stuck our climb buttons onto our algae mode just because we didn't want to make a whole new controller mode just for climb sequence. So yeah. Yeah, so you can see the LEDs go blue. That's an indication to the driver that both the limit switches have been triggered. And as Shory mentioned earlier, that will initiate an auto climb sequence.
All right, folks, that was your look at this incredible 254 machine. This is one of the most impressive robots of the year. And we want to thank you guys so much for allowing us to come by and have a look at this machine. And good luck with the rest of your competition.
Thanks for watching. Don't forget to like, subscribe, and click the bell to stay up to date on future fun videos. First Team SolidWorks is free for you. Design in 3D, build your robot, and gain the career-ready skills 80% of employers look for when hiring engineers. Get SolidWorks for your entire team when you go to solidworks.com/first.